All right, so here's the last part of our lesson for today. And this example's, I don't want to say difficult, it's just not as linear as other examples are. So we're going to be discussing a little bit of properties of vectors that we're creating and then verifying that we've done the right thing. And it will make more sense when I actually write out the question. So example number 3, bear with me while I copy this. Discuss the following vectors with respect to collinearity and a word that I don't say very often, so coplanarity. So whether they're collinear or not, or coplanar or not, and we'll have to find three vectors that form the basis for space, and we're going to write the fourth vector as a linear combination of the other three. Okay, so obviously don't try it yet because I haven't given you the vectors yet. So I've got vector u is going to be nice and simple 1, 1, and 1. Vector w, 1, 0, and minus 1. Vector v will be, what do I have here? 1, 2, and 3, oh, comma, 3. And then finally, vector x will be minus 1, minus 1, and 1. Okay? So, take a minute. You don't even necessarily have to write anything, but like think mentally yourself or write it down if you want to. Are these linear, or sorry, collinear? Are they coplanar? How do you know? How can you verify? Okay? So, we're going to start off with no two vectors from this list are collinear. Now, you can 100% do the calculation to check, but just because of the nature of the simplicity, let me finish writing this, so no scalar multiple factor, of these vectors, we can just do this by inspection, right? Because the I value, for example, for u is 1. It's the same for w and it's the same for v. So at least, let's pretend x doesn't exist right now. At least for these three, I can't multiply u by anything to make it equivalent to the other two, because the moment I multiply u by anything, I'm going to change the value of I, and therefore the I values aren't going to line up, and I would be doing that at the expense of trying to get the j and the k values to line up. So basically, right now the I values line up and everything else doesn't, but if I try to make everything else line up, then by default I'm going to be changing the value of I, so then that won't line up anymore. So that's not going to work. And then if I multiply by negative 1, this will become negative 1, this will become negative 1, but so will this 1. So this also doesn't work. And it's equally true for the other two. Basically, just there's no scalar multiple factor that works for any of the vectors, so none of them are collinear. Okay? Now, we know they're not collinear now. We didn't do the calculation, like I said, because of the simplicity. Now let's see if they're coplanar. So, to test if something's coplanar or not, so coplanarity, sorry if I'm butchering the pronunciation there, I'm going to do U cross V and then dot W, okay? Right, because U cross V will give me a vector and dot W, and depending on what that value is, we'll know if they're coplanar or not, right? If it's essentially either 0 or any other value other than 0, okay? So first, let's just do this over here. That's why I left a little gap over here, so we can just have it on hand for us. We're just going to do U cross V, and I'm actually going to do it with two different methods because I've just had multiple people come up and ask me why this method works but this other method doesn't. So the method that I showed you in class, I'll do here in blue ink, is this one, which ironically enough, even though I showed it to you in class, it's actually not the one I use the most often, but it's the easiest one to not make a mistake on, even if it costs me a little bit more time. So I write each of the vectors that I'm crossing twice. I eliminate this here, so I'm getting rid of the most left column and the most right column. And now my I component is going to be 1 times 3 minus 2 times 1. So my first component will be 3 minus 2, so it'll just be 1, comma. Then here, sorry, 1 times 1 will just give me 1 minus 3 times 1, so it's going to give me negative 2. And then for the last component, 1 times 2 will give me 2, minus 1 times 1 is just 1, so I'll just be left with 1. So that's the method I showed you in class, and on it, you of course don't even have to write this part, you can do it mentally, but if you do write it, it is a little more time consuming, but it's not time consuming enough to be a detriment to any evaluation that you're writing. But I know a bunch of people in the class have been using this method. So it's like essentially finding the determinant of a matrix if you watch that on your own time. So I would still write the two vectors. I've got 1, 1, and 1, and then 1, 2, and 3. And a good way to visualize what's happening here is imagine you're covering stuff up. So for my I component, I'm taking this first column. Let me line it up with the camera. It's like I'm covering up that left column. And I'm doing the same operation. I'm doing 1 times 3 minus 2 times 1. So that's going to give me 3 minus 2. It's still just going to give me 1. Then, imagine that I can cover up this middle column over here. So I'm just left with the leftmost and just left with the rightmost. Now I'm going to have 1 times 3, which will be 3, minus 1 times 1. So it's going to give me 2. And now now imagine I'm covering up the rightmost column. So again, just a visual aid. You're covering up one column at once, or one at a time, and then you're doing the same operation. So now it's 1 times 2, which is 2, minus 1. So this will give me 1. And you'll notice a discrepancy between the answer I have here and the answer I have here. So if you're using this method, all you have to remember is always flip the sign of only the j value, and it will give us the same thing. Okay? And ironically, this is the method that I use the most often. Okay? So it's the one I didn't show you in class. Just because we haven't introduced matrices yet to you, so it wouldn't make as much sense as this one. Okay? But either method is fine. Just remember to flip the sign of j if you use this method over here. Okay? Now that we have the vector of u cross v, now we can dot it with w and see if it gives a 0 or not. So let's do that over here. Plugging in u cross v, I've got 1, negative 2, and 1, dot. What's my value for w? Just copying it, 1, 0, and negative 1. And now, nice and easy, 1 times 1 is 1. 0 times -2 or -2 times 0 is irrelevant, right? Because plus or minus 0 doesn't change anything. And then 1 times -1 is -1. So the positive and the -1 cancel out, and the 0 remains. So we're left with 0. And now, therefore, u, v, and w, because these are the 3 vectors I used to do this test, are coplanar. Awesome. And now all we have to do is see what x is. So we're going to do the exact same operation we did with the cross between u and v, but now instead of dotting it with w, we're just going to dot it with x to see what we get. So I'll just write it. I'll just name it test number 2. And I'll do for vector x. Same idea. U cross v using the value that we already got, dot with x. So 1 minus 2 and 1 dot -1, -1, and 1. Okay. And now when I do the dot product here, 1 times -1 will give me -1. -2 times -1 will give me +2. And +1 times +1 will give me +1. And kind of similar to what we had last time, the 1's cancel out, but now my middle term is no longer a 0. It's equal to 2. So therefore, u and v is not on the same plane as vector x. Okay? And because they're not on the same plane of vector x, that by definition means that the 3 vectors form the basis for space. The 3 vectors that form the basis for space are u, v, and x. Okay? And now there's a second part to our question, but again, I just don't want the video to run too long, so please, just for the last section, click on the last video in the playlist.